The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, and welcome to Engineering Resilience Through Chaos with our guest speaker today, Russ Miles. I'm Adele Green and I'm the Community Manager here at eSynergy Solutions. We help organisations to build technical teams and capability through our communities. Now, before we begin, if you have any questions for Russ, please fire them over via the questions box and Russ will answer them at the end of his talk. We are recording the session and this will be made available tomorrow via email. So now I'm going to hand over to Russ to begin the presentation.
So hello everyone, can you actually hear me okay? Do you want to confirm that they can hear me? I better check this. Yes, it looks like I'm on okay. Let me keep the cursor in. Right, welcome everyone. Thank you very much for your time this afternoon, this morning, this evening, this late night, possibly if you're dialing in from around the globe. So what I'm going to talk about today is engineering resilience through chaos engineering as a discipline. Thank you to eSynergy Solutions for working with us to put this together. It's exciting to be able to share with you some of what we do with our customers when they're trying to do chaos, and really start maybe share some of the war stories and experiences we've had along the way. If you aren't familiar with who we are, I'm the one on the left speaking right now. I'm the co-founder of Chaos IQ, and Sylvain Hellegouache on the right there is our CTO. We've been around for about a year now as a company operating mostly in Europe, and we work with a lot of mostly large enterprises as they approach using chaos engineering, or at least how they comprehend it, and then they begin to practice it and eventually mature their disciplines internally. Okay, this has obviously been put together with the wonderful folks at eSynergy Solutions, who have very much encouraged us to get out there and tell the world what we're doing with chaos engineering. And that's pretty much the way our partnership with eSynergy works. So we're very happy with that, and it's great to be involved with them. Okay, this talk, if I've been told to use the term, is a whirlwind tour. I think there's something to be said about whirlwinds, that they probably aren't always a good thing. So hopefully this what I share with you today won't end up causing quite as much destruction as something like that typical type of tornado whirlwind would. But it will be a very fast tour, so it's a very fast glance, if you like, at all of the different aspects of chaos engineering. And to be fair, what I've distilled down is probably around 5 years of experience of doing these things, and at least a year now of building tools in this space to help companies get better at doing chaos engineering themselves. So bear in mind, you've got about 45 minutes that's been distilled from 5 years, and you'll get an idea of just the sort of whirlwind we're going to embark upon. So to get us started with, I like to use this model. This is Kinevin. This is just a way of thinking about the systems that we tend to build. And the bad news is that most systems, if they're useful, and certainly if they're in an enterprise of any size, are just not in the bottom right quadrant. You're just not doing simple systems, I'm afraid. So if you're not there, then if we move around the block a little, we end up thinking that maybe we're doing complicated systems. And complicated systems are something that are attractive to us because they do have good practices. Someone can come in and say, do this, and maybe it'll work for you. So with a bit of context, you might be doing the right thing in a complicated system. But there's bad news on the horizon as well, because if you're building anything that you would call distributed, if you have external dependencies, or if you're cloud native, or frankly, if you're just a modern system that has a lot of moving parts, then you probably aren't in complicated anymore. You're down over there in complex. And complex is okay, but it's in the nature of the beast. Some of the downsides of being in complex is that, generally speaking, the rule is if you have a complex system, if you need to look after that system, the system looking after it has to be 5 times more complex than the system itself. So difficult place to be, but we can still survive and we can still work with these systems. And in fact, they are probably necessarily complex. So that would be okay to be there, but we have, as you might be already anticipating, some more bad news for you. Systems that evolve quickly, well, that's what we generally build these days. We're supposed to be agile, and agile means that we are constantly putting our systems under the pressure of change and continuous delivery. So when you do that, you tend to drift, unfortunately, into the chaotic and drift into failure in that bottom left quadrant there. So that's not the place we'd like to be. So one of the first rules of chaos engineering is we're not introducing chaos. We're not engineering chaos. We're trying to engineer ourselves out of chaos. And in this respect, back to the Mealy complex. So when you look at that sort of story, it's tempting to sit back and go, couldn't we just design things better? Couldn't we maybe, with a bit more thought, come up with just a simpler system? Could we prevent this whole problem and not have to do anything new, not add anything new to our toolbox? Unfortunately, we can't. When you build a complex system, it's usually essentially complex. And that means by being that complex, it tends to have what we call dark debt. The thing about dark debt is you just don't know it's there. It really is the surprise stuff. And I like this definition by John Allspaw, which is, dark debt cannot be anticipated or prevented. This is not a design out philosophy. It is a natural byproduct of complexity. We build very complex systems, and so there is always the chance that dark debt is ready and there to bite us. And we don't know it's there until something dramatic happens. The challenge here is that we're building systems that evolve quickly. And not only do the users want feature velocity from us, we want to be able to innovate quicker than our competitors, their users also need absolute reliability. They would like the systems to always be there. They would like not to know that we're experiencing difficulties even if we are. So users will generally don't just want that level of reliability, but they actually need it. The other side of this is that you probably need that reliability as you work on the systems that you're responsible for, that you own. In fact, you could argue ownership implies that you're trying to introduce and look after the reliability of your system as well. And this is where it gets straight into the pockets of the business, because 1 hour of downtime, as quoted, is at least $100,000 for 95% of enterprises. By the way, that number gets a lot worse if you are in the business of media. The quoted figure for media companies is that you're looking at about $1 million an hour. And this is lost revenue and lost end user productivity. So this is direct onto the business. This isn't even the woolly stuff. This isn't the, regulatory non-compliance fees or goodwill that you might have lost from your users. This is hardline what it costs us when our systems go down. If we start to include those other figures as well, we start to get even worse figures. So this is something that I think everyone in a business can understand, is that outages, system failures, and system reliability, they all relate directly to the money in the bank. So what can you do with this is going on? If you are a responsible system builder, participant in a system, what can you do to do better at this? The idea here is you can invest in resilience. Resilience is the system property. It's the collective socio-technical system capability that can try to meet the reliability constraints that we're trying to work for our users. So the answer really is we need to invest in resilience to get to the reliability in the systems that our users expect, whilst not holding back that ever-present friction and stress of change. And the thing about resilience is, at its heart, it's a learning loop. It's about people learning how to do better within the system they're working. So let's look at what that means. You have a system that you could label as normal. So you've built a system, you've got it running, you think it's okay, and then bang, an outage happens. And ideally, it isn't the user that notices first that there has been an outage, but arguably someone has noticed there's a problem. And since the whole place is on fire, then we better do something about it. We shift then into crisis mode. certainly our brains do, and we go straight into a detection, diagnosis, and fix cycle where you're probably working with your colleagues under extreme stress to try to fix the problem. And then after time, after having got to some sort of fix, you might then ideally go into a exercise and cycle around learning about what actually happened and seeing if you can improve the system such that it isn't just fixed, but perhaps it's been improved as well. And that improvement, if it's a technical improvement, tends to be an improvement in simple system robustness. But also robustness can be introduced in the people, the practices and processes around the system as well. Now, there's lots of theory, so there's only many years of research into how this sort of learning loop can be best executed. But the main point about this is that it starts really with the alert signals going off that an outage has occurred. And that's where we get the phrase in resilience engineering, where we say never let an outage go to waste. So an outage is an opportunity. It's an opportunity to learn and improve. But let's also be honest, an outage is a rather dramatic way to learn. And in fact, during an outage is the worst time to learn for our brains. So you could argue that we might be able to do better than relying on outages alone. So post-mortem, post the outage, learning is a good idea. However, pre-mortem learning is probably a little bit better. It would be nice to be able to do more than just rely on outages to trigger us to learn and improve. So over to my friend Bertrand Russell there. Wouldn't it be great if there was a proactive practice for exploring and diminishing system weaknesses before they affect users? Well, that, of course, is what chaos engineering is all about. Chaos engineering, in this quote here from Michael Barrett, allows us to have pre-mortems, things that we do in advance of the potential post-mortems, to explore, to try to surface and discover weaknesses in our systems before they affect our users. And in fact, that's pretty much the definition that comes from the wonderful principles of chaos. Chaos engineering is the discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions. The only word there I would tone down just a touch, I think, as a refinement, is distributed. I don't think it has to be a distributed system to benefit from this pre-mortem exploration and discovery of weaknesses. Clearly, there are a lot more potential failure modes, perhaps, in a distributed system, particularly a large-scale one, but you could argue that any system of any sufficient complexity where there may be this dark debt hanging around would benefit from a little light being thrown on that debt before it bites us in the heat of an outage. So this is what chaos engineering as a learning loop tends to look like. We start with something that we perceive as normal, a system that we perceive as operating within its tolerances. We then do some sort of exercise, a chaos engineering exercise, such as a game day, which is a manual experiment where a team and potentially observers look at what happens when something may occur. Or we could do an automated chaos experiment where we maybe want to run the experiment completely automatedly and possibly frequently to see how the system responds under those turbulent conditions that it causes. Then we can look at how we detect, how we diagnose, how we fix, how the systems are surrounding this often very small scale chaos could actually respond to all of these triggers. And then finally, we cycle round to learning again. And now we're learning on the basis of something we've deliberately and carefully controlled to do against the system. It's not in the immediate heat of the outage. This is something that we knew we were going to do. And although there may have been an impact on the system, we now have a way of learning from it and improving the system. And again, improving the overall system's robustness. So we can learn after outages, but it's even better if we can learn from weaknesses before an outage. And that is what chaos engineering is for me. One of the great analogies I think that has been used out there is by Colton Andrews of Gremlin. It says that it's a bit like getting a flu shot. When you get a flu shot, you get a small amount of essentially the disease, of the harm into our system, enough for us to get better, to improve, to build up the robustness of our body in reaction to these things. So when that actual disaster of potentially catching flu occurs, our system is ready for it. And that's, when you think about it, that's a great analogy for the turbulent conditions in production, where we're injecting a little bit of those turbulent conditions and we're getting better as an overall system, the people, the practices, the processes, the technologies involved, everything, how that system responds to those small scale disasters so that we can get better when the bigger scale ones may happen. And this is how I like to view it in terms of how chaos affects the potential failure modes across an entire system. The interesting thing to point out here is that most people are familiar with infrastructure level chaos through things like Chaos Monkey, but there are many, many other vectors for introducing potential failure across an entire stack, and of course the whole socio-technical system, including the people, practices, and processes. In fact, one could argue that the majority of system failures, certainly ones that hit the headlines, seem to gravitate around the people, the practices, and the processes, and the conditions within which they have to work. And that's probably not surprising, because people are fallible. We just are. And we need to build systems that accommodate and support that fallibility. But if we don't ever explore the potential of it, the only time we're going to see it is when we have a catastrophic failure, and then the temptation is to blame the individual rather than learn from the exercise. And this kind of leads us into why culture matters so much when we're talking about chaos engineering. You see, it's tempting to set up chaos engineering as an external factor, that is a group of people perhaps that are there to hurt your systems. And in my experience, that's been the easiest way for chaos engineering to fail in an organization. If you set up a group, like perhaps you have done in the past for a security penetration testing group, if you set up a chaos group on the side, and what they do is they begin to look at experiments and ways of exploring weaknesses in other people's systems, what you'll soon realize is that those people running those systems will see that chaos group as a group they don't want to deal with. They're a group that they'll try and game against. They're a group that they'll have a conflict relationship with. And that really is poison to the learning that's supposed to happen through that chaos engineering learning loop. So my preference is to set things up pretty much the way I believe it's set up in Netflix, which is the chaos group really doesn't execute chaos themselves against other people's systems. What they do is support, educate, and provide tooling to the people that own those systems so that they can own their own chaos. They can do it themselves. And that's a key facet, I think. It's a very collaborative exercise, and anyone who takes on either the responsibility or even the participation in a chaos engineering group needs to be working with everyone else that owns the systems to help them explore the weaknesses, rather than becoming an outside party that executes chaos against the system. I mean, the joking phrase I use there is, if you're in any way inclined to execute chaos against someone else's system, you're not a chaos engineer anymore, you're just a sadist. So how do we get started doing chaos engineering? One of the techniques I use, there are lots of ways of starting, but one of the ways I found pretty useful to get everyone to step back and observe their system under the critical light of what could fail is using something like a very lightweight version of failure modes and effects analysis. This is an old technique, it's been around for a very long time in the operations catalog, if you will. And it helps us step back and ask ourselves the questions, what could fail, without anyone getting too defensive. One of the dangers when you're looking at a system and trying to figure out what could go wrong is that the people responsible for perhaps some of those architectural or technical decisions are often inclined to get quite defensive, understandably, because they feel like they're under criticism. This exercise that I run generally avoids that sort of reaction of defensiveness. And this is how it tends to play out. Number one, I get everyone in the room to identify what they would agree as what I tend to call illities. So things that we care about, things that the business will find important to know about our system. So the system needs to have an availability level. It needs to be able to recover. It needs to be able to scale. And all of those abilities are then played out as a list. And it's really just a taxonomy for us to think this is what matters to our system. We can agree that these facets are important. These are things that we need to contribute to when we discover where the weaknesses are. So when we look at a weakness, we will know it's a weakness that relates to scalability or it relates to availability. Number two, then I try to get everybody involved to discover what are the actual parts of the system that we can recognize. And these can be very low level, they can be relatively high level, but either way, we end up with a vocabulary to describe the system as we have it. And sometimes we sketch out a big diagram on the wall that says these are the parts as we see it. Simon Brown has written a great book on how you do sketching to discover and explore architectures. Thoroughly recommend that as a book to grab when you're going through this exercise, particularly at this point. Step three is where it gets interesting. We start to describe specific failures, and it's a very an inoffensive way of doing it. I want everyone to get very specific and say this could happen. Sometimes those things happen based upon past experiences, and sometimes they are things that are just off the top blue sky thinking of what could go wrong. However, the important part is they're incredibly specific. They're not just general, oh, well, we could have a security breach. It's more along the lines of we could have a network failure of this particular node in this way, in this part of our system. And so you get extremely specific ideas of where the failures might be. Then, as you can see in the picture, we put it on a chart where we see along the top impact and along the side likelihood. So we're trying then just to get an idea of what the big impact failures might be, the specific ones, and then the likelihood of that particular impact being a risk on our system. That gives us a way of then deciding what action to take next. Which of those failures could we explore that would give us a bit of confidence that we can handle that sort of failure, particularly if it's a big impact, high likelihood one. One of the other things you can do is you can then label those post-its that include your failures with back to the illities, back to the things that matter. So when you're talking to non-technical stakeholders, you don't just say, well, we're worried about the network node dying in this way with this latency. You can say this, we believe this maps back to gaining confidence. If we would explore this, we would gain confidence in perhaps recoverability, perhaps security, perhaps latency of the system. We would have a collection of really valuable qualities to that highly technical failure that we've described. So that's how we get down to the level of failures that we could then explore with chaos engineering. And chaos engineering is a natural next step to do pre-mortems on these potential failures. Two things you can do. One of them is a game day, and I thoroughly recommend that everyone after this call should be doing game days, not literally straight now, but certainly planning to do them in the next couple of days. Game days are, to describe them quickly, it's like playing Dungeons & Dragons with your colleagues. What you do is you set up certain conditions, often in staging, of that particular failure that you want to explore. You set it as a very small impact blast radius, we tend to call it in chaos engineering, effect, and then you see how everyone deals. You can explore everything from how good your playbooks are. You can explore whether people know where the playbooks actually are indeed. You can also explore if anyone knows where the passwords are. You can explore a number of scenarios and weaknesses, not only at the technical, but certainly at the social level as well, by doing a game day. What we're going to focus on for the rest of this session, though, is if you were to then explore these things with a chaos experiment, with an automated chaos experiment. The flow from game days to chaos experiments tends to occur where game days are really easy to set up, very simple to get going, but you can't run them all the time. Now, if you think about it, those transient conditions in production, those turbulent transient conditions, they're changing all the time. And the difficulty is if you only once a week or once a fortnight explore weaknesses against the system, and perhaps not even in production, then you're never really getting a chance to try out all the different options, and you're not getting that opportunity to throw the light on the dark debt that you would do if you could continuously run the chaos. Now, chaos engineering is one of those continuous techniques. Just like continuous delivery and continuous integration, we have continuous chaos. But you can't continuously run game days because, well, frankly, we have other work to do. So automation is a natural next step. Once you have some valuable experiments that either surface weaknesses or did surface weaknesses in the past that you've now overcome, then it's a good idea to think about whether those should graduate into being automated chaos experiments. And in fact, what I've noticed as people mature using chaos engineering, they sometimes leap straight to doing automated chaos experiments for quite a few of the weaknesses they want to explore. So let's do a real-world experiment, and it truly is a real-world experiment. It's something that we collaborated with one of our customers on. What that customer had was some dark debt in Kubernetes. Sounds awful, doesn't it? But it wasn't quite as bad as perhaps you might realize, but it was an interesting story because it actually was a socio-technical weakness in the system. It was a combination of the people and the practice and the processes and the facilities that the technology offered. So this is how it was set up. You have a number of development teams that are owning their apps and services in a Kubernetes cluster. And then you also have, in the bottom right there, some cluster admins, and they have a different set of responsibilities. Their responsibilities are to manage the cluster's resources, the nodes and other bits and pieces that often and frequently cost money to have. So these two groups, which is a typical split when you're running Kubernetes, have absolutely valid jobs, but there is danger of there being miscommunication between the two groups. As soon as you have two groups that happen to be disconnected from one another in any way, you always have the ability for there to be miscommunication, and that was the case here. You see, the story that played out is that the teams would set up their specifications to run their apps and services appropriately with the selected level of redundancy in the system that they wanted, and the cluster admins during their normal daily work would of course occasionally upgrade nodes, take down resources, bring them out, put them back. Normal operations. But there is a weakness in this, in the sense that the teams could ask for a certain level of redundancy across running multiple instances of their services, and if the cluster admins are doing their job and they remove a node, it could leave a service starved of the resources it needs. Now, there is a facility in Kubernetes to basically protect against this, to actually give the cluster admins a hint that they're about to take something out that will leave the apps and services that the application development teams on the top left, what they ask for can no longer be honored. And so there is a facility there, but often it's not used. And this was the case in this particular customer. So they had a Kubernetes system that was set up appropriately with two groups of people trying to do the right thing, but because they'd missed a potential weakness, then there was the opportunity for failure to come about. So we built an experiment to explore this. This is one of the tickets that went up on the wall. It was the what if when we ask a certain specification for our application to deploy to Kubernetes, it gets what it needs, but then someone takes a node out of action. What happens to our needs at that point? We built the experiment using the free and open source Chaos Toolkit. You can go and grab it now. It's easy to use, and I'll talk a little bit later about how you can extend it as well. We use the toolkits for a number of reasons, but it was also because it was to hand, and it's the project we've worked on now for over a year. The way it works is that, first of all, we have a title and description of the experiment we're going to explore. So that's usually along the lines of, let's go and look at this system and see if it can handle a node being drained out of it without accidentally starving the application services of the resources they need. So we have a title and description. We also then describe a contribution. Now, the contribution maps back to those utilities. I'm a big fan of having, in an experiment, it declaring its contribution back to our overall business needs, and also describing why it's useful in the first place. So the title and description is nice, but the contribution should speak straight back to the business, say this is what we're building trust and confidence in. Then we have a steady state hypothesis. Steady state hypothesis declares what normality should look like on the system. It says when we look at the system and we probe it, we should see certain conditions within certain tolerances. If we see those, we are in what we declare as being a known normal state. Bear in mind that any system at any time could be under the stress of change, parts of it could be failing, but as long as those probes of the steady state hypothesis are still met, we still declare it as being within tolerance and therefore a recognizable steady state. Then we have a method. The method is where the harm is injected, where going back to the flu shot analogy, where we apply the vaccine. We try something small, we limit the blast radius of what we're doing, but we make some amendment to the running system that hopefully introduces the sort of turbulent conditions that we're trying to figure out, do those affect the steady state hypothesis? And then last of all, we'll also define potentially some rollbacks, which are just mechanisms to put back what we know we have damaged. The flow for using an experiment made out of these concepts is they start with a title and description, we have a contribution, and then we have a steady state hypothesis. The steady state hypothesis, as we execute the execution, this very first thing that we do is checking, should we do the experiment at all? At this point, if we don't recognize the system is in a steady state, then we shouldn't go and do any experiment against it. You shouldn't be doing experiments against a dirty Petri dish. So this is the point at which you can make that decision. So that's the first job of the steady state, is to decide, should we even be doing an experiment against the system in the state that it's currently in? Assuming we pass that, then we go ahead and do the method, which introduces the turbulent conditions, and then we use the steady state hypothesis again, which tells us, have we deviated? Now, as chaos engineers, when we're doing chaos experimentation, we celebrate when there is a deviation, because we found a weakness, or at least we found potentially the indicator of a weakness. And we can then look at what improvements might need to be made to the system based upon the experiment we've done. It's quite different from chaos testing. Chaos testing is when we're automatically running chaos experiments all the time, and we want them to pass, for there to be no deviation. That's more of a validation exercise. Now, in terms of how you write the experiment, it's probably the same. It's just that when you're using the experiment at first, you're probably more involved in experimentation itself, where you're trying to explore and discover surface weaknesses. And then later on, you're probably looking to make sure that none of those weaknesses have re-arisen. Okay, so now the last thing we can do is any rollbacks, which, like I say, is just putting anything back the way where it's kind of like a finally block in most programming languages. We're just going to put back the pieces that we know we destroyed. Now, I'm a little bit sensitive around the word rollbacks, because when you run a chaos experiment, bearing in mind, particularly if you're doing experimentation, you're trying to discover new knowledge. And so by definition, you might, and in fact, you're trying to find something surprising, something that deviates from what you expected, something that deviates from the steady state hypothesis. So rollback is a bit of a strange term here. We're not really rolling the system back to an absolute known state. In fact, you can't, because you don't know what you're going to discover. So my preference, although it's a much more complicated phrase, is to call rollbacks, or at least to think of rollbacks as remediating actions. They're the things we do to fix things back the way we think they were, and certainly according to the things we changed. But bearing in mind that an experiment is supposed to elicit new knowledge, it's supposed to give us something new, then in fact, there is no such thing as a perfectly safe experiment, because if it's perfectly safe, it's not an experiment, it's a test. Okay, so let's look at how we implement an experiment using the Chaos Toolkit. Chaos Toolkit has two main ways of expressing an experiment. You can do it in JSON, or you can do it in YAML. There's also, certainly floating around on the tickets on the open source project, there's the idea of potentially having a fluent programmatic approach to doing it as well. This is what we have for now. So you declare your experiment. This is your first step, which is you have a title, a description, and then we can move rapidly into what is our steady state hypothesis. In this case, our steady state hypothesis is that the application will respond normally when we hit a particular URL. And we're also looking at Kubernetes and a particular set of pods in it and going, you should be in this phase. If either of those conditions aren't met, then if we test this before we do the method of our experiment, then we could declare that the system is not in a recognizable normal state, so we shouldn't do the experiment. If we compare this to the system after the method has completed, then we could say it has deviated and we may have found a weakness. The method for our experiment is actually quite short. All it needs to do is go in, pretend it's an administrator, a cluster admin, and go ahead and take out a particular node, which it does. It drains a node off of the system. And what that'll do in our case is if we haven't introduced any features to protect the applications and services from this sort of operation, we could leave the system where all the pods are not in the appropriate state, and that's why our steady state hypothesis would then fail. Okay, the last thing we have is our rollbacks. In the case of rollbacks, you can imagine it's literally the opposite of our method. We're going to then take the node that we've drained off, we're going to uncoordinate, put it back in the system. That's the best at this point that we can do. That's as much remediating action as we can take. Okay, so we would run that experiment, and we certainly did, and we found a weakness, and then we overcame it using Kubernetes disruption budgets. If you want to see the full sample, it's actually in a repo that I linked to earlier in the presentation, and when we put the email out after this session, you'll be able to have the link in there to the sample so you can look at running it yourselves. And just now to picture out what the Chaos Toolkit has done for us, it gives you the power to express using this experiment vocabulary the experiments that you want to run. We then customize the toolkit because the toolkit really is an orchestrator of chaos. Underneath, we have drivers that integrate with a number of systems out of the box to be able to probe and introduce chaos to those systems as part of your experiments. So the Chaos Toolkit is eminently extendable with drivers and even with plugins. Plugins are different. Plugins are ways that the toolkit can communicate to other systems to say, this is what's happening in the chaos that we're running. So for example, we use a Slack plugin. So the free and open source Chaos Toolkit, you can run an experiment and you can see your experiments being the progress of them popping up in Slack as well. Okay, so the Chaos Toolkit gives us a tick in the box for automation. It means you as an individual can go ahead and write your experiments, orchestrate them across your systems. You can extend it your way with whatever system you're using. And that's what we've seen a lot of people in the community doing, is turning around saying, we're using the Chaos Toolkit, we've created our own drivers if we needed to, or we've just used the fact that they can call through to a process, and we're using all of the chaos systems or failure injection that we already had, but now we're orchestrating it with a toolkit. So that's great because it lifts everyone up to be able to look at experiments rather than just the damaging effects that are being applied to the systems. One of the comments we get back is now we have a common vocabulary of chaos experimentation captured in those experiment definitions. So that's really great. But that's not the whole story, not by a long way. You see, we're trying to provide tools that support you doing chaos engineering. And back to that role of what a chaos engineering group or people with that responsibility, how they have to operate. They're supposed to be providing support, educating, and providing tooling to all of the teams, and maybe they're part of those teams that are doing chaos against their own systems. So there's a lot more that is necessary to take a toolkit and say in any way that it provides everything that chaos engineers might need. And for that, we've gone a bit further. We've created the Chaos Platform. Chaos Platform is broken up into several pieces that meet the needs of what we see as a professional chaos engineering capability in an organization. Number one in that is a control plane, something that you can orchestrate, schedule, inspect, and work with the chaos experiments across an entire organization. Something that supports the collaboration of teams, so that you can see organizations, teams, and permissions across an entire system. One of the other things that you quickly realize when you're doing chaos in a larger enterprise is that you need observability. Everyone needs to be aware of the chaos that's being run. And one of the great cases that we've been looking at is how you can know that chaos is happening and in some cases subdue alerts from a particular part of a system so that it will not start complaining because we know it's under chaos at a given moment in time. And the last one, and we were lucky in this regard, because we build on top of the Chaos Toolkit and the open source projects that that accompany it, you can customize the whole thing your way. And this is one of the big things that we've seen, is that most of the customers we're working with, they want to run chaos their way in their organization. And so the chaos platform we put together, building on top of the Chaos Toolkit, really gives them that power to give their own chaos people the ability to build and customize using the chaos platform to achieve their own customized chaos platform to meet their needs, to then apply that to everything everyone else actually needs in their unique context. So that's most of what I wanted to share with you today to get the conversation going. The chaos platform is really the enterprise option that we have. It does all the job that somebody may need to actually customize it to their needs within their company. The Chaos Toolkit is out there, free and easy to use, and please go and play with it. You can get started with chaos engineering right now, and that is something I would recommend you do this evening. We've got some upcoming conferences that both myself and Sylvain are speaking at and will be at. So if you're in DevOpsCon Munich, or in fact, if you're in Build Stuff Lithuania, or in fact, if you are at NewCon in London, then you'll be able to catch up with me. Sylvain is going to KubeCon Seattle because we're working extremely closely with the CNCF on how they capture chaos engineering for the working group there. There's also announced yesterday, I pointed out that we've got a couple of O'Reilly Safari online courses on chaos engineering. So if you've been, if your appetite has been whetted by the discussion today, and you want to jump into actually doing some chaos with me on those courses, then please go sign up. And there's also a book that will be out very soon. It's likely to be a free online book, which is an open source automated chaos engineering book that's coming very soon as well. I think at this point, I'm going to see if anyone has any questions they want to ask coming out of the main presentation. Do we have any questions at all? Adele, I can't see any at the moment. Am I looking in the wrong place? I'm still looking for the questions at the moment. I'm not seeing any right now. One question I can discuss, I suppose, is one I hear an awful lot, which is, how do I know I'm ready to do chaos engineering? And do I need to do anything to actually be ready to do it? Is there any sort of low minimum bar that I need to get going? And I would always argue that there's really no minimum bar to doing chaos engineering. And in fact, you could start thinking about chaos engineering even before you have anything built. Thinking about failure is something that can be done the moment you even conceive of an architecture. So I would argue the mindset's applicable from the word go. But then you start to look at actually building experiments once you have absolutely anything in what you would call production. There's no real minimum bar. There are certainly system capabilities that grow in maturity alongside chaos engineering. The first one tends to be observability. That is certainly increased rapidly. Other things that tend to increase rapidly, certainly people will develop playbooks quicker once they know that chaos is coming. People become aware of failure as part of the job of dealing with the system. Certainly, failure becomes an unignorable quantity. So I would always say to start doing chaos engineering almost immediately, that you start conceive of the system, because there's never too early to start considering failure. I've had a question come through. What is the book mentioned for architectural sketching? It's a book by Simon Brown. It's on LeanPub. I'm trying to recall the name. If you give me just a moment, I will look for what that name actually is. Here we go. So there is Software Architecture for Developers is a great collection of books that talk about how to sketch and work through system architecture and communicate it effectively. So Simon is an absolute legend in this particular area, and he's well worth speaking to if you find him at conferences, and these books are well worth grabbing. Okay, so that probably leaves it for me just to turn my screen sharing back on and to suggest if anyone wants to get in contact, please do. You can jump onto the Chaos Toolkit Slack at join.chaostoolkit.org and ask me any questions there anytime at all. Pop us an email at contact@chaosiq.io if you're beginning your journey towards chaos engineering, or even if you already have a mature chaos platform of your own and you would really like us to look at it and see if we can take some of the burden of running it off of your shoulders. Either way, hope to stay in contact, and good luck with your chaos engineering journey. Thank you very much.